Greetings, this is Greg. The most famous Allied airplane of the First World War has to be the Sopwith Camel. It's not that it was the best one, probably not even second best, but it has several accolades that no other Allied fighter can match. Let's go through them. Perhaps most importantly, it shot down more enemy aircraft than any other Allied airplane. A pilot flying a Sopwith Camel may have shot down the Red Baron and is often credited with doing so. The Sopwith Camel helped turn the tide and ended what I'll call the Albatross era, which was a period from the fall of 1916 until mid-1917, during which time the German Albatross fighters were winning the air war. In April of 1917, often called Bloody April, German aircraft shot down 245 Allied aircraft, causing 400 casualties for a loss of only 66 of their own airplanes. Once the Sopwith Camel started to show up in significant numbers, the Royal Flying Corps was able to turn the tide. In popular culture, Snoopy flew a Sopwith Camel, which is the reason a lot of people who don't know anything about aviation have at least heard of the airplane. In technical terms, there really wasn't anything revolutionary about the Camel. It was an evolutionary step forward from the Sopwith Pup. The Pup was certainly a good airplane, at least as good as any other fighter when it was introduced in late 1916, but it did not give the Royal Flying Corps enough of an edge to end the Albatross era. The Camel did. The name Camel comes from the metal fairing over the two cowl-mounted machine guns, creating a hump. Myself, I don't really see it. It's not much of a hump, certainly not very camel-like. However, pilots of the time saw the hump and started calling it the Camel, and the name stuck. Officially, this plane is the Sopwith F1, which was the most common variant of the plane. There were some others, a shipboard variant and a two-seater and more, but in this video we are only covering the F1 variant, and although it was never officially called the Camel, that's the name I'll use. This was the first Allied plane to carry two forward-firing synchronized machine guns from the factory. Up until this point, Allied fighters, both British and French, had a single machine gun synchronized to fire through the propeller, at least normally. Some of these fighters were pretty good airplanes, for example, the French Spad 7, the Nieuport 17, along with the British Sopwith Pup and triplane. However, all of these planes from the factory had a single synchronized machine gun. Some Sopwith triplanes were said to have been modified with twin guns, and of course it wasn't uncommon to put a Lewis gun on the top wing of a Nieuport 17, but a single synchronized machine gun was the standard and common configuration for Allied fighters prior to the Camel. The German Albatross, both the early D2 and D3 models, had twin guns, giving them a huge advantage in firepower. Twice the firepower means on average you only have to keep your sights on target for half the time. The disparity may have been even worse. Some sources say that the German Spandaus, when synchronized to fire through the propeller, put out 450 rounds per minute, and the British Vickers only 300 under these conditions. If that's true, it means that the Albatross had 3 times the firepower of a Sopwith Pup. It's not only about firepower. Another advantage of the twin guns is that if one jams, which apparently happened quite a bit, you're not out of the fight while you try to clear it. You still have one more gun that's still working. The Sopwith Camel finally gave the Allied fighter pilots something with 2 synchronized machine guns. The hump cover over the guns was not structural. It wasn't there for aerodynamics. It was just a piece of metal that was put there in an effort to trap engine heat and keep the guns warm. Apparently they could freeze up at altitude and stop working. I've never figured out why this did not seem to be a design consideration on other World War I fighters. Maybe it was. Perhaps the liquid-cooled airplanes had so much more engine heat that the relative location of the guns eliminated the problem. Maybe the other air-cooled fighters handled this in a way I just can't see, via engine compartment exhaust heat or something else. I'm just not sure. Anyway, on the Camel, that hump is functional, so now you know. The Camel's wings were conventional for the time, but it had a lot of wing area, giving it a lower wing loading than any other Allied fighter except for the Sopwith Pup. After the Pup, Sopwith came out with their triplane. The Camel came next, and interestingly, the Sopwith triplane and Camel have exactly the same amount of wing area, but the Camel is the lighter airplane, although only slightly. The only German airplane with a lower wing loading than the Camel was the Fokker DR-1, and it was only slightly lower. The DR-1 also has a slightly lower stall speed based on the best information that I have. That does make sense, as the DR-1 has slightly lower wing loading and a more advanced wing design. I have a video about that if you're interested, link in the description. I should mention that most of this data comes from NASA's book, Quest for Performance. The Sopwith Camel is on the cover, along with the P-51 Mustang and the XB-70. This cover really tells a story. The Sopwith Camel first flew only 24 years before the P-51 Mustang, which in turn first flew only 24 years before the Mach 3 capable XB-70. 48 years between the Sopwith Camel and the XB-70. I find that to be amazing. I do have this book in the Patreon section. Back to our story. I guess there are a few things special about the Camel's wing. The dihedral is interesting. It has quite a bit of dihedral on the bottom wing, but none on the top wing. That was unusual. It's not some secret aerodynamic trickery. It was done to simplify construction of the top wing. The Camel has ailerons on the top and bottom wing. That was the normal British way of doing things. Put an aileron on every wing. The Sopwith triplane has them on all wings. The German planes usually only had them on the top wing. However, the German planes tended to use comparatively larger ailerons. I've never seen an explanation for these different philosophies. I think it's likely that the Germans went with big ailerons on one wing to simplify construction, and the British just felt that they needed ailerons on all wings. One upgrade to the Camel's wing structure, or maybe it would be better to say wing support, was the use of streamlined bracing wires known as RAF wires, sometimes just spelled RAF wire. In World War I, these were used exclusively on British airplanes, including the previous fighters from Sopwith. The bracing wires were not just round wires as typically used in other airplanes. They were more flat and directional, sort of like the shape of a symmetrical airfoil but pointing into the relative wind. I don't have any pictures of these, so you'll have to use your imagination. I'm curious how the modelers handle this, because some of those guys are really serious about accuracy. Max probably knows about this. Most of the Camel was constructed via very conventional, but for the time, well-proven methods. The designers crammed everything heavy into the first 7 feet of the fuselage. The engine, oil tank, pilot, guns, ammunition, and fuel tank. This resulted in about 90% of the aircraft's loaded weight packed into the first 7 feet, or 2.1 meters of the airplane's length. The pilot's feet were actually below the rearward components of the engine, specifically right under the oil pump, and the guns are above his legs and the fuel tank right behind him. A Camel is not a good plane to be in if you crash, but this configuration helps control response and agility due to the low polar moment of inertia. We need to talk about the Camel's engines. The vast majority of these were powered by the 130 horsepower Clerget 9B rotary engine. It's spelled Clerget. Some Camels were powered by the Bentley BR-1 with 150 horsepower. I don't have production numbers for Camels with different engines, but it appears that very few Camels were built with the Bentley engine, and possibly only the naval variants, so no F1s. For the rest of this video, I'll focus on the 130 horsepower Clerget 9B. I mentioned earlier, this is a rotary engine, not the type of rotary found in some sporty Mazdas. The Mazda, or more correctly called the Wankel engine, are totally different and have nothing to do with the original type of rotary engines from World War I aviation. If we look at an air-cooled engine from the World War II era, it's almost always a radial, meaning that the cylinders are arranged radially from the center of the engine where the crankshaft is located. Of course, the crankshaft spins and delivers power to the propeller. A World War I era rotary, so not a radial, but a rotary, looks similar. The big difference is that the crankshaft on a rotary is stationary and the entire engine spins around it, hence the name. There are a lot of drawbacks to this. First of all, it throws oil everywhere as these engines were not sealed. Do you see any valve covers on this engine? No, you do not. The oil flows up to the rocker arms, and the centrifugal effect of the spinning engine slings the oil off from there. It throws oil out at a rate of about 1 gallon an hour, or about 3.8 liters, and it makes an incredible mess. The spinning engine also complicates the connections for fuel, oil, and everything else that doesn't spin, which causes those sort of things to be prone to leaks. The centrifugal effect tries to pull the entire engine apart, which seriously limits the maximum possible RPM, which also affected the propeller design of rotary-engined airplanes. Then there are the gyroscopic forces, which I'll get to, and those complicate the pilot's job. So if rotary engines have all of these problems, why were they so popular in World War I? It's because at the time there were two technical problems that converged to cause the extensive use of these rotary engines. The first was that air-cooled engines of the period tended to overheat. Piston engines, especially with these power levels, were new, and materials and manufacturing just didn't quite keep up. The second problem was the relatively low speeds of World War I airplanes. The planes had trouble moving fast enough to provide all of the cooling airflow the engines needed. A rotary engine spins and thus has airflow through the cooling fins independent of aircraft speed. From the moment it starts up, it's getting a lot of cooling airflow. Rotaries died out shortly after the First World War because airplanes were getting faster and the cooling fins and other parts of the engine became more advanced. They got better. The ultimate Achilles heel of the rotary was the centrifugal effect trying to pull it apart. As you build a larger and more powerful engine, this becomes a bigger and bigger problem. As post-war engines got bigger and more powerful, the rotaries just couldn't keep up in power anymore, and the whole idea died out rather suddenly. One of the notable features of the rotary engine, and especially when it's in a Sopwith Camel, was the way the gyroscopic forces would affect the plane's flying characteristics. The Camel was famously tricky to fly, and as we will see, that's caused by a combination of two things: gyroscopic precession and the plane's very concentrated center of mass. All propeller-driven airplanes have gyroscopic forces that affect yaw and pitch. Rotary engine airplanes have much stronger gyroscopic forces because the entire engine spins along with the propeller. In aviation, this is called gyroscopic precession. I find that a lot of people don't understand this, and it's a bit hard to explain, but it's worth understanding as it relates to more than spinning engines. It relates to bicycles, motorcycles, really anything with a spinning wheel or disc of some sort. If you're a flight sim pilot of World War I airplanes, at least of flight sims that are accurately modeled, this information is going to help you as well. A spinning disc, like a propeller, or in this case a propeller and a rotary engine bolted to it, will exhibit gyroscopic effects. There are two fundamental principles of gyroscopic action: rigidity in space and precession. It's precession that we're interested in right now. Here is the rule, and it's a bit odd. Anytime a force is applied to a spinning disk out of its plane of rotation, the resulting force is 90 degrees ahead of and in the direction of rotation and in the direction of application. I know that's confusing, but I hope it makes sense in just a few minutes. We're going to go through this. I'm sure we all know that the plane rotates about its three axes. It rolls around the longitudinal axis, yaws about the vertical, and pitches about the lateral axis. Gyroscopic precession only relates directly to pitch and yaw, not roll. The Camel's Clerget engine spins clockwise as viewed from the rear. Take a look at this picture. The propeller in this Cessna spins the same direction. As the tail is raised in this airplane, in other words, as the plane pitches down, this has the effect of pushing the top of the propeller forward. So the affecting force in this picture is pushing forward on the top of the propeller. However, that pushing force is seen 90 degrees from where you pushed it in the direction of rotation. So if you look at the propeller from the rear, that would be at about the 3 o'clock position. Because that force is being seen at the 3 o'clock position, it will try to move that portion of the propeller forward, and this will yaw the plane to the left around the vertical axis. Thus, in a tail dragger like a Sopwith Camel, when you raise the tail on takeoff, you're pushing the top of the propeller forward. but that force is seen as a push at the 3 o'clock position, and it will yaw the nose to the left. Conversely, when you raise the nose, you push the bottom of the propeller forward. That will yaw the nose to the right. Gyroscopic precession is not affected by roll, and it does not directly affect roll either, only pitch and yaw. Of course, it can indirectly affect roll because if it causes yaw, the plane will tend to roll in the same direction. So if pitching up or down, gyroscopic precession will cause the plane to yaw. Conversely, yawing the plane via the rudder pedals will cause the plane to pitch either up or down. For example, yawing to the right will push the left side of the prop forward, which will cause a pitch down force. At this point, you should be able to visualize this effect. If we push on the prop via pitch or yaw, that force will be seen 90 degrees in the direction of rotation and in the direction the force was applied. So any pitching of the airplane will cause a yawing force from gyroscopic precession, and any yawing put in will cause a pitching force from it. Of course, these forces can be mixed. You could be rotating the plane in pitch and yaw at the same time. This is sort of what happens in a turn, and we're going to look at that soon. In most propeller-driven airplanes, the entire engine is not spinning, so the effects of gyroscopic precession are not huge. In the Camel, they are, and this is exaggerated by several things. First, you have a 380-pound engine spinning up there, not just the propeller. Second, on takeoff, you're at fairly low speed when the controls don't have a lot of airflow over them. This is a big part of what makes the Camel so tricky to fly, especially on takeoff. The way pilots deal with this is by raising the tail slowly and countering with rudder. If you raise it slowly enough, that yawing force will be manageable. What about all this talk about the plane turning better to the right than the left? Well, that's true, but it's often said that it's due to the torque of the engine. It's not. It's due to gyroscopic precession. Torque affects roll, not turning, related but different. Consider a plane in a right-hand turn with around 45 degrees of bank. We're pushing forward on that spinning disc on the portion that's on the outside of the turn. In other words, the plane is rotating about both the vertical and lateral axis. Thus, the force being put on the prop is a combination of what we saw from just pitch or yaw alone. We will see that force 90 degrees clockwise as viewed from the rear, which will push the nose down and yaw us to the right. That's not really a problem. We're already pulling back on the stick because we're in a turn, so having to pull back more is not a big deal. The yaw to the right isn't terrible either. Worst case, the nose drops a bit from the yaw and the plane speeds up. There isn't much risk of loss of control here. In a right turn in the Camel, gyroscopic precession means a bit less right rudder and a bit more pull on the stick. A left turn is much more tricky. Now that force is still moving the nose to the right, but now there's an upward component to it, opposite of what we had in the right turn. In this scenario, we'll need an unusual amount of left rudder and a relatively forward stick to counteract it. This is unnatural to a pilot when in a left turn, and if not handled quickly, the nose moving up will increase the gyroscopic force while causing the plane to slow down, thus reducing the effectiveness of the rudder and elevator needed to counter it. All of this makes rotary engine airplanes a bit tricky to fly, and the Camel even more so because of its highly concentrated center of mass. That makes it easier to induce a pitch or yawing motion, which is what gyroscopic precession does. Thus, the Camel was tricky to fly, and its superior turn rate to the right does make sense, although it's not that the gyroscopic forces were really helping it there, it's just that they made the turns to the left comparatively difficult. It's also possible that below a certain speed, the controls would not be able to counter the gyroscopic forces below a certain speed in an aggressive left-hand turn. Could the pilot use these gyroscopic forces to rapidly maneuver the airplane? Well, not in coordinated flight, so not in normal flying climbs, sustained turns, those sort of things. But when you get into slips, skids, spins, snap rolls, and some other maneuvers that involve uncoordinated flight for relatively short periods of time, then yes, absolutely, a skilled pilot could take advantage of this. There are airshow pilots who manage to do a double hammerhead, and one of those pilots made a video showing exactly how gyroscopic forces can be used to make this happen. I'll put a link to that in the video description. I believe I can make a strong case, very strong case, that at least one World War I pilot had mastered this. That is, mastered using gyroscopic precession to his advantage in a dogfight, not doing a double hammerhead. I don't think any World War I airplane would have survived that. Thus, I think it's likely that some other World War I pilots had mastered this idea as well. As for the Camel, well, it's tricky to fly. The pilot is poorly protected in a crash, even by World War I standards, and it's not particularly fast. It did have good climb performance, maneuverability, firepower, and dive speed. Overall, it was superior to the main German frontline fighter at the time, which was the Albatros, usually either the D3, D5, or D5A variant. It was the Camel, more than any other British type, that enabled the Royal Flying Corps to wrest control of the air from the Germans. I know they also had the SE-5A, and yes, it was very good. But those came into service at a slow rate. The heavier burden was on the Camel in mid to late 1917. The Camels shot down more enemy aircraft than any other Allied type during the war. I know that I said that earlier, but it's important. Sopwith went on to create many other airplanes. Their ultimate World War I fighter was the Sopwith Snipe, and after the war they became Hawker. I talk about that in my video on the Hawker Sea Fury. I'll link that in the description. Please consider joining my Patreon. Members there often get early access to videos, as well as access to pilot manuals and other documents I use in the creation of these videos. Please like and subscribe. Goodbye, and have a great day.